A scintillator is a material that exhibits scintillation, the property of luminescence when excited by ionizing radiation. Luminescent materials, when struck by an incoming particle, absorb its energy and scintillate. Sometimes, the excited state is metastable, so the relaxation back down from the excited state to lower states is delayed. The process then corresponds to either one of two phenomena, depending on the type of transition and hence the wavelength of the emitted optical photon, delayed fluorescence or phosphorescence, also called afterglow. Principle of operation: a scintillation detector or scintillation counter is obtained when a scintillator is coupled to an electronic light sensor such as a photomultiplier tube, photodiode, or silicon photomultiplier. PMTs absorb the light emitted by the scintillator and re-emit it in the form of electrons via the photoelectric effect. The subsequent multiplication of those electrons results in an electrical pulse which can then be analyzed and yield meaningful information about the particle that originally struck the scintillator. Vacuum photodiodes are similar but do not amplify the signal, while silicon photodiodes, on the other hand, detect incoming photons by the excitation of charge carriers directly in the silicon. Silicon photomultipliers consist of an array of photodiodes which are reverse biased with sufficient voltage to operate in avalanche mode, enabling each pixel of the array to be sensitive to single photons. History: the first device which used a scintillator was built in 1903 by Sir William Crookes and used a ZNS screen. The scintillations produced by the screen were visible to the naked eye if viewed by a microscope in a darkened room. The device was known as a spinthariscope. The technique led to a number of important discoveries but was obviously tedious. Scintillators gained additional attention in 1944, when Curran and Baker replaced the naked eye measurement with the newly developed PMT. This was the birth of the modern scintillation detector. Applications for scintillators: scintillators are used by the American government as Homeland Security radiation detectors. Scintillators can also be used in neutron and high-energy particle physics experiments, new energy resource exploration, X-ray security, nuclear cameras, computed tomography and gas exploration. Other applications of scintillators include CT scanners and gamma cameras in medical diagnostics, and screens in older-style CRT computer monitors and television sets. The use of a scintillator in conjunction with a photomultiplier tube finds wide use in handheld survey meters used for detecting and measuring radioactive contamination and monitoring nuclear material. Scintillators generate light in fluorescent tubes. Scintillation detectors are also used in the petroleum industry as detectors for gamma-ray logs. Properties of scintillators: there are many desired properties of scintillators, such as high density, fast operation speed, low cost, radiation hardness, production capability and durability of operational parameters. High density reduces the material size of showers for high-energy I-cubed quanta and electrons. The range of Compton's scattered photons for lower-energy I-cubed rays is also decreased via high-density materials. This results in high segmentation of the detector and leads to better spatial resolution. Usually high-density materials have heavy ions in the lattice, significantly increasing the photofraction. The increased photofraction is important for some applications such as positron emission tomography. High stopping power for electromagnetic component of the ionizing radiation needs greater photofraction. This allows for a compact detector. High operating speed is needed for good resolution of spectra. Precision of time measurement with a scintillation detector is proportional to a ISC. Short decay times are important for the measurement of time intervals and for the operation in fast coincidence circuits. High density and fast response time can allow detection of rare events in particle physics. Particle energy deposited in the material of a scintillator is proportional to the Scintillator unregistered trademark S response. Charged particles, I-cubed quanta and ions have different slopes when their response is measured. Thus, scintillators could be used to identify various types of I-cubed quanta and particles and fluxes of mixed radiation. Another consideration of scintillators is the cost of producing them. Most crystal scintillators require high-purity chemicals and sometimes rare earth metals that are fairly expensive. Not only are the materials an expenditure, but many crystals require expensive furnaces and almost 6 months of growth and analyzing time. Currently, other scintillators are being researched for reduced production cost. Several other properties are also desirable in a good detector scintillator: a low gamma output, transparency to its own scintillation light, efficient detection of the radiation being studied, a high stopping power, good linearity over a wide range of energy, a short rise time for fast timing applications, a short decay time to reduce detector dead time and accommodate high event rates, emission in a spectral range matching the spectral sensitivity of existing PMTs, an index of refraction near that of glass to allow optimum coupling to the PMT window. Ruggedness and good behavior under high temperature may be desirable where resistance to vibration and high temperature is necessary. The practical choice of a scintillator material is usually a compromise among those properties to best fit a given application. Among the properties listed above, the light outputs is the most important, as it affects both the efficiency and the resolution of the detector. The light outputs is a strong function of the type of incident particle or photon and of its energy, which therefore strongly influences the type of scintillation material to be used for a particular application. The presence of quenching effects results in reduced light output. Quenching refers to all radiationless de-excitation processes in which the excitation is degraded mainly to heat. The overall signal production efficiency of the detector, however, also depends on the quantum efficiency of the PMT, and on the efficiency of light transmission and collection. The light outputs is often quantified as a number of scintillation photons produced per keV of deposited energy. Typical numbers are, a per mil 40 photons keV for nano TL, 10 photons keV for plastic scintillators, and 4 photons keV for bismuth germanate. Scintillation detectors are generally assumed to be linear. This assumption is based on two requirements: that the light output of the scintillator is proportional to the energy of the incident radiation, that the electrical pulse produced by the photomultiplier tube is proportional to the emitted scintillation light. The linearity assumption is usually a good rough approximation, although deviations can occur. Resistance and good behavior under high temperature, high vibration environments is especially important for applications such as oil exploration. For most scintillators, light output depends on the temperature. This dependence can largely be ignored for room temperature applications since it is usually weak. The dependence on the temperature is also weaker for organic scintillators than it is for inorganic crystals, such as NaITL or BGO. The coupled PMTs also exhibit temperature sensitivity, and can be damaged if submitted to mechanical shock. Hence, high-temperature rugged PMTs should be used for high-temperature, high-vibration applications. The time evolution of the number of emitted scintillation photons N in a single scintillation event can often be described by linear superposition of 1 or 2 exponential decays. For 2 decays, we have the form where IF and IS are the fast and the slow decay constants. Many scintillators are characterized by 2 time components, one fast, the other slow. While the fast component usually dominates, the relative amplitude A and B of the 2 components depend on the scintillating material. Both of these components can also be a function of the energy loss dx. In cases where this energy loss dependence is strong, the overall decay time constant varies with the type of incident particle. Such scintillators enable pulse shape discrimination, that is, particle identification based on the decay characteristics of the PMT electric pulse. For instance, when BiF2 is used, I-cubed rays typically excite the fast component, while I+ or minus particles excite the slow component. It is thus possible to identify them based on the decay time of the PMT signal. Types of scintillators: organic crystals. Organic scintillators are aromatic hydrocarbon compounds which contain benzene ring structures interlinked in various ways. Their luminescence typically decays within a few nanoseconds. Some organic scintillators are pure crystals. The most common types are anthracene, scorbin, and naphthalene. They are very durable, but their response is anisotropic, and they cannot be easily machined, nor can they be grown in large sizes. Hence they are not very often used. Anthracene has the highest light output of all organic scintillators and is therefore chosen as a reference. The light outputs of other scintillators are sometimes expressed as a percent of anthracene light. Organic liquids, these are liquid solutions of one or more organic scintillators in an organic solvent. The typical solutes are fluors such as p-terphenyl, PBD, butyl PBD, PPO, and wavelength shifters such as POPOP. The most widely used solvents are toluene, xylene, benzene, phenylcyclohexane, trithylbenzene, and decaene. Liquid scintillators are easily loaded with other additives such as wavelength shifters to match the spectral sensitivity range of a particular PMT, or 10B to increase the neutron detection efficiency of the scintillation counter itself. For many liquids, dissolved oxygen can act as a quenching agent and lead to reduced light output, hence the necessity to seal the solution in an oxygen-free, airtight enclosure. Plastic scintillators. The term plastic scintillator typically refers to a scintillating material in which the primary fluorescent emitter, called a fluor, is suspended in the base, a solid polymer matrix. While this combination is typically accomplished through the dissolution of the fluor prior to bulk polymerization, the fluor is sometimes associated with the polymer directly either covalently or through coordination, as is the case with many Li-6 plastic scintillators. Polyethylene naphthalate has been found to exhibit scintillation by itself without any additives and is expected to replace existing plastic scintillators due to higher performance and lower price. The advantages of plastic scintillators include fairly high light output and a relatively quick signal, with a decay time of 4 nanoseconds, but perhaps the biggest advantage of plastic scintillators is their ability to be shaped, through the use of molds or other means, into almost any desired form with what is often a high degree of durability. Plastic scintillators are known to show light output saturation when the energy density is large. Bases. The most common bases are the aromatic plastics, polymers with aromatic rings as pendant groups along the polymer backbone, amongst which polyvinyltoluene and polystyrene are the most prominent. While the base does fluoresce in the presence of ionizing radiation, its low yield and negligible transparency to its own emission make the use of fluors necessary in the construction of a practical scintillator. Aside from the aromatic plastics, the most common base is polymethyl methacrylate, which carries two advantages over many other bases: high ultraviolet and visible light transparency and mechanical properties and higher durability with respect to brittleness. The lack of fluorescence associated with PMMA is often compensated through the addition of an aromatic co-solvent, usually naphthalene. A plastic scintillator based on PMMA in this way boasts transparency to its own radiation, helping to ensure uniform collection of light. Other common bases include polyvinyl xylene polymethyl, 2,4-dimethyl, 2,4,5-trimethylstyrenes, polyvinyl diphenyl, polyvinyl naphthalene, polyvinyl tetrahydronaphthalene, and copolymers of these and other bases. Fluors, also known as luminophores, these compounds absorb the scintillation of the base and then emit at larger wavelength, effectively converting the ultraviolet radiation of the base into the more easily transferred visible light. Further increasing the attenuation length can be accomplished through the addition of a second fluor, referred to as a spectrum shifter or converter, often resulting in the emission of blue or green light. Common fluors include polyphenol hydrocarbons, oxazole and oxadiazole aryls, especially N-terphenyl, 2,5-diphenyloxazole, 1,4-D, 5-phenyl 2-oxazolyl, benzene, 2-phenyl 5,4-biphenylyl, -1, 3,4-oxadiazole, and 2,4-1 registered trademark tert-butylphenyl, -5, 4-1 registered trademark A-1 registered trademark biphenylyl, -1, 3,4-oxadiazole. Inorganic crystals. Inorganic scintillators are usually crystals grown in high-temperature furnaces, for example, alkali metal halides, often with a small amount of activator impurity. The most widely used is NaI-TL. Other inorganic alkali halide crystals are CSI, TL, CSI, Na, CSI, Pure, CSF, Ki, Tl, Li, U. Some non-alkali crystals include BaF2, KF2, U, ZNS, Ag, KWO4, CdWO4, YAG, say, GSO, LSO. Newly developed products include LaCl3, say, lanthanum chloride doped with cerium, as well as a cerium-doped lanthanum bromide, LaBr3, say. They are both very hygroscopic but offer excellent light output and energy resolution versus 38 photons keV for Ni, Tl, a fast response versus 230 nanoseconds for Ni, Tl, excellent linearity, and a very stable light output over a wide range of temperatures. In addition, LaBr3, say, offers a higher stopping power for I-cubed rays. LYSO has an even higher density, is non-hygroscopic, and has a higher light output than BGO, in addition to being rather fast. A disadvantage of some inorganic crystals, for example, Ni, is their hygroscopicity, a property which requires them to be housed in an airtight enclosure to protect them from moisture. CSI, Tl, and BaF2 are only slightly hygroscopic and do not usually need protection. CSF, Ni, Tl, LaCl3, say, LaBr3, say, are hygroscopic, while BGO, KF2, U, LYSO, and YAG, say, are not. Inorganic crystals can be cut to small sizes and arranged in an array configuration so as to provide position sensitivity. Such arrays are often used in medical physics or security applications to detect X-rays or I-cubed rays. High-Z, high-density materials are typically preferred for this type of applications. Scintillation in inorganic crystals is typically slower than in organic ones, ranging typically from 1.48 nanoseconds for ZNO, Ga, to 6,000 nanoseconds for KWO4. Exceptions are CSF, fast BaF2, as well as the newer products, 28 nanoseconds. LaBr3, say, 16 nanoseconds. LYSO, 41 nanoseconds. Gaseous scintillators. Gaseous scintillators consist of nitrogen and the noble gases helium, argon, krypton, and xenon, with helium and xenon receiving the most attention. The scintillation process is due to the de-excitation of single atoms excited by the passage of an incoming particle. This de-excitation is very rapid, so the detector response is quite fast. Coating the walls of the container with a wavelength shifter is generally necessary as those gases typically emit in the ultraviolet and PMTs respond better to the visible blue-green region. In nuclear physics, gaseous detectors have been used to detect fission fragments or heavy charged particles. Glasses. The most common glass scintillators are cerium-activated lithium or boron silicates. Since both lithium and boron have large neutron cross-sections, glass detectors are particularly well suited to the detection of thermal neutrons. Lithium is more widely used than boron since it has a greater energy release on capturing a neutron and therefore greater light output. Glass scintillators are however sensitive to electrons and I-cubed rays as well. Being very robust, they are also well suited to harsh environmental conditions. Their response time is a per mil 10 nanoseconds, their light output is however low, typically a per mil 30% of that of anthracene. Physics of scintillation. Organic scintillators. Transitions made by the free valence electrons of the molecules are responsible for the production of scintillation light in organic crystals. These electrons are associated with the whole molecule rather than any particular atom and occupy the so-called molecular orbitals. The ground state SO is a singlet state above which are the excited singlet states, the lowest triplet state, and its excited levels. A fine structure corresponding to molecular vibrational modes is associated with each of those electron levels. The energy spacing between electron levels is a per mil 1 eV. The spacing between the vibrational levels is about 1/10 of that for electron levels. An incoming particle can excite either an electron level or a vibrational level. The singlet excitations immediately decay to the S state without the emission of radiation. The S state then decays to the ground state SO by emitting a scintillation photon. This is the prompt component or fluorescence. The transparency of the scintillator to the emitted photon is due to the fact that the energy of the photon is less than that required for a SA or SO transition. When one of the triplet states gets excited, it immediately decays to the TO state with no emission of radiation. Since the TOA or SO transition is very improbable, the TO state instead decays by interacting with another TO molecule, and leaves one of the molecules in the S state, which then decays to SO with the release of a scintillation photon. Since the TO-TO interaction takes time, the scintillation light is delayed. This is the slow or delayed component. Sometimes, a direct TOA or SO transition occurs, and corresponds to the phenomenon of phosphorescence. Organic scintillators can be dissolved in inorganic solvent to form either a liquid or plastic scintillator. The scintillation process is the same as described for organic crystals. What differs is the mechanism of energy absorption. Energy is first absorbed by the solvent, then passed on to the scintillation solute. In organic scintillators, the scintillation process in inorganic materials is due to the electronic band structure found in crystals and is not molecular in nature, as is the case with organic scintillators. An incoming particle can excite an electron from the valence band to either the conduction band or the exciton band. This leaves an associated hole behind, in the valence band. Impurities create electronic levels in the forbidden gap. The excitons are loosely bound electron hole pairs which wander through the crystal lattice until they are captured as a whole by impurity centers. The latter then rapidly de-excite by emitting scintillation light. The activator impurities are typically chosen so that the emitted light is in the visible range or near UV where photomultipliers are effective. The holes associated with electrons in the conduction band are independent from the latter. Those holes and electrons are captured successively by impurity centers exciting certain metastable states not accessible to the excitons. The delayed de-excitation of those metastable impurity states again results in scintillation light. BGO is a pure inorganic scintillator without any activator impurity. There, the scintillation process is due to an optical transition of the B3+ ion, a major constituent of the crystal. A similar process exists in CdWO4. Gases. In gases, the scintillation process is due to the de-excitation of single atoms excited by the passage of an incoming particle. Response to various radiations, heavy ions. Scintillation counters are usually not ideal for the detection of heavy ions for three reasons. The very high ionizing power of heavy ions induces quenching effects which result in a reduced light output. For example, for equal energies, a proton will produce 1/4 to 1/2 the light of an electron, while alphas will produce only about 1/10 the light. The high dx also results in a reduction of the fast component relative to the slow component, increasing detector dead time. Strong nonlinearities are observed in the detector response, especially at lower energies. The reduction in light outputs is stronger for organics than for inorganic crystals. Therefore, where needed, inorganic crystals, for example CSI, TL, ZNS, Ag, KF2, U, should be preferred to organic materials. Typical applications are I+ or- survey instruments, dosimetry instruments, and heavy ion dx detectors. Gaseous scintillators have also been used in nuclear physics experiments. Electrons. The detection efficiency for electrons is essentially 100% for most scintillators. But because electrons can make large-angle scatterings, they can exit the detector without depositing their full energy in it. The backscattering is a rapidly increasing function of the atomic number Z of the scintillator material. Organic scintillators, having a lower Z than inorganic crystals, are therefore best suited for the detection of low-energy beta particles. The situation is different for high-energy electrons, since they mostly lose their energy by Bremsstrahlung at the higher energies. A higher Z material is better suited for the detection of the Bremsstrahlung photon and the production of the electromagnetic shower which it can induce. Gamma rays. High Z materials, for example inorganic crystals, are best suited for the detection of gamma rays. The three basic ways that a gamma ray interacts with matter are: the photoelectric effect, Compton scattering, and pair production. The photon is completely absorbed in photoelectric effect and pair production, while only partial energy is deposited in any given Compton scattering. The cross-section for the photoelectric process is proportional to Z5, that for pair production proportional to Z2, whereas Compton scattering goes roughly as ZA high Z material therefore favors the former two processes, enabling the detection of the full energy of the gamma ray. Neutrons. Since the neutron is not charged, it does not interact via the Coulomb force and therefore does not ionize the scintillation material. It must first transfer some or all of its energy via the strong force to a charged atomic nucleus. The positively charged nucleus then produces ionization. Fast neutrons primarily rely on the recoil proton in reactions. Materials rich in hydrogen, for example plastic scintillators, are therefore best suited for their detection. Slow neutrons rely on nuclear reactions such as the OR reactions, to produce ionization. Their mean free path is therefore quite large unless the scintillator material contains nuclides having a high cross-section. For these nuclear reactions such as 6Li or 10B materials such as Li, U, or glass silicates are therefore particularly well suited for the detection of slow neutrons. List of inorganic scintillators. The following is a list of commonly used inorganic crystals. BaF2 or barium fluoride. BaF2 contains a very fast and a slow component. The fast scintillation light is emitted in the UV band and has a 0.7 nanoseconds decay time, while the slow scintillation light is emitted at longer wavelengths and has a 630 nanoseconds decay time. It is used for fast timing applications, as well as applications for which pulse shape discrimination is needed. The light yield of BaF2 is about 12 photons keV. BaF2 is not hygroscopic. CaF2, U, or calcium fluoride doped with europium, the material is not hygroscopic, has a 940 nanoseconds decay time, and is relatively low Z. The latter property makes it ideal for detection of low-energy I-squared particles because of low backscattering, but not very suitable for I-cube detection. Thin layers of CaF2, U, have also been used with a thicker slab of NaI-TL, to make phosphors capable of discriminating between I plus or minus, I-squared, and I-cubed particles. BGO or bismuth germanate. Bismuth germanate has a higher stopping power, but a lower optical yield than NaI-TL. It is often used in coincidence detectors for detecting back-to-back gamma rays emitted upon positron inhalation in positron emission tomography machines. CdWO4 or cadmium tungstate, a high-density, high atomic number scintillator with a very long decay time, and relatively high light output. CdWO4 is routinely used for X-ray detection. Having very little 228 and 226 Ra contamination, it is also suitable for low-activity counting applications. CaWO4 or calcium tungstate, CSI, TL, or cesium iodide doped with thallium, these crystals are one of the brightest scintillators. The maximum wavelength of light emission is rather high, however, making CSI, TL, best coupled to red-enhanced PMTs or to photodiodes. CSI, TL, is only slightly hygroscopic and does not usually require an airtight enclosure. CSI, Na, or cesium iodide doped with sodium, the crystal is less bright than CSI, TL, but comparable in light output to NaI, TL. The wavelength of maximum emission is at 420 nm, well matched to the photocathode sensitivity of Bialcali PMTs. It has a slightly shorter decay time than CSI, TL. CSI, Na, is hygroscopic and needs an airtight enclosure for protection against moisture. CSI, and doped cesium iodide emits predominantly at 315 nm, is only slightly hygroscopic, and has a very short decay time, making it suitable for fast timing applications. The light output is quite low, however, and very sensitive to variations in temperature. GD202S or gadolinium oxysulfide is a high stopping power due to its relatively high density and the high atomic number of gadolinium. The light output is also good, making it useful as a scintillator for X-ray imaging applications. LaBr3, say, a better alternative to NaN-TL. Denser, more efficient, much faster, having a decay time about 20 nanoseconds, offers superior energy resolution due to its very high light output. Moreover, the light output is very stable and quite high over a very wide range of temperatures, making it particularly attractive for high-temperature applications. Depending on the application, the intrinsic activity of 138 La can be a disadvantage. LaBr3, say, is very hygroscopic. LaCl3, say, very fast, high light output. LaCl3, say, is a cheaper alternative to LaBr3, say. It is also quite hygroscopic. PbWo4 or lead tungstate, due to its high Z, PbWo4 is suitable for applications where a high stopping power is required. Lu-I3 or lutetium iodide, LSO or lutetium oxyorthosilicate, used in positron emission tomography because it exhibits properties similar to bismuth germanate, but with a higher light yield. Its only disadvantage is the intrinsic background from the beta decay of natural 176 Lu. LYSO, comparable in density to BGO, but much faster and with much higher light output. Excellent for medical imaging applications. LYSO is non-hygroscopic. NaN-TL, or sodium iodide doped with thallium, NaN-TL, is by far the most widely used scintillator material. It is available in single crystal form or the more rugged polycrystalline form. Other applications include nuclear medicine, basic research, environmental monitoring, and aerial surveys. NaN-TL is very hygroscopic and needs to be housed in an airtight enclosure. YAG, say, or yttrium aluminum garnet, YAG, say, is non-hygroscopic. The wavelength of maximum emission is at 550 nm, well matched to red-resistive PMTs or photodiodes. It is relatively fast. Its light output is about one-third of that of NaN-TL. The material exhibits some properties that make it particularly attractive for electron microscopy applications. ZNS, Ag, or zinc sulfide, ZNS, Ag, is one of the older inorganic scintillators involved as ZNS screen. It is only available as a polycrystalline powder, however. Its use is therefore limited to thin screens used primarily for I+ or minus particle detection. ZnWO4 or zinc tungstate, see also, gamma spectroscopy, liquid scintillation counting, scintillation counter, scintillating bolometer, neutron detection, total absorption spectroscopy. References. Bibliography, Leo, WRA Euro-OE Techniques for Nuclear and Particle Physics Experiments Euro, 2nd edition, Springer, ISBN 354057280, Duclos, Stephen J., Scintillator Phosphors for Medical Imagining, External Links, Crystal Clear Collaboration at CERN, Gamma Ray and Neutron Spectrometer, Scintillation Crystals and Their General Characteristics, Scintillation Properties, from Lawrence Berkeley National Laboratory.